Welcome to class meeting 22nd of EECE574. We've taken quiz 2, but one of the students hasn't yet taken due to excuse the absence. So please do not discuss on the quiz with him. Got it? Handouts, lecture videos are available from the primary web page. No special corrections. And here goes the overview. So we are covering stochastic convergence and the limit theorem part. And last time we started to study the equality of two real or complex valued functions. I made some corrections, but the basic idea is like this. So suppose you are given two functions, x and y, that has domain 1, domain 2, and range 1 and range 2. When you are given two functions, the first thing for you to talk about the equality of two functions is that the domains are the same. Otherwise, you can never say two functions are the same. Second, of course, the ranges must be in the some same superset. In this case, we assume they are subsets of the real set. That's why we call the function x and y are real functions. Here, real functions means real valued functions, which means range 1 and range 2 are subsets of the real set. Got it? So if we change the topic to the to complex valued functions, this part will be changed to the set of complex numbers. Got it? So be careful. Here, the domain D may be a subset of real, but in general, it is an abstract set. However, without loss of generality, we are going to assume this domain as an uncountable set. For example, the interval 0 to 1. Got it? Or the entire real line. So given two real or complex valued functions, x and y, the first thing for us to talk about equality, the domains must be the same. And if two functions are real valued, ranges are the subsets of real numbers. That are necessary conditions. Then here goes first the equality everywhere and the equality almost everywhere definitions. So two functions x in D2, let me simply say R without no problem when you talk about this. So given two real valued functions, x equals y if blah blah blah. Here, if is the if and only if in the definition. Okay, in the definition, if you say if, it's only an if and only if. If what? First, for less in the domain, you have the same value. So if the set D, the domain D, is an uncountable set, you have how many equalities of two real numbers? Uncountably infinite number of two real numbers equality you need to check. That is the definition. And here goes the notation. We say x equals y everywhere. Sorry, x equals y everywhere. Actually, everywhere on the common domain. Got it? And this is the definition and notation. And sometimes we simply just say x equals y, parenthesis e, everywhere. Or sometimes just without parenthesis, e dot, something like that. Some people even put e on top of equality. There are many notations. This definition can be modified, even though it's not popular, in many different ways. So equivalent definitions. This part goes the same if. Now we are going to replace uncountably infinite equality into a set equality. So here goes the set S in D, where X and Y have the same value equals D. What does that mean? For every S in D, you check whether this holds or not. And if equality holds, that S is the member of this set. And it turns out that every S in D is in the set. Got it? So without exception, they are the same. And here goes another one. You may say definition or alternate definition of equivalent definition. If, of course, they are different. Equals, this notation is the empty set. Okay, this is called the empty set. This is not phi, actually. If you use LaTeX or latex, this is empty set, something like that. And phi looks like this, and the empty set looks like that, or is it change it? Anyway, so they are different. Do not confuse when you use LaTeX. Anyway, so everywhere equality is very simple. Now we define almost everywhere equality, and as the name says, it's about almost everywhere equality. So given two functions having the same domain, in our case, two real functions, x equals y almost everywhere if blah, blah, blah. And this definition is kind of changing, not this one, but that one, or that one. So here goes the definition. You again check you test every member of the domain, and you check whether each S in D is a member of that set or not. And here we relax a little bit. That set could be smaller than the domain D. However, if you measure the size of the set, it's the same as the measure of the size D. Got it? For example, let D as the interval from 0 to 1. And you have a function, a straight line, for example. This is x of s. And y of s is also same as that one, except two endpoints. Then let me ask you, what is that set? This set is the open interval 0, 1. So this is definitely not the domain, but a proper subset of the domain. Now you take the measure of that set. It's still 1, and your original domain also has measure, the length in this case, 1. So we can say x and y are equal almost everywhere on D, actually. Got it? Of course, this kind of case is very typical, but not fully representing every case like this. So you should be careful. But anyway, this is the truth. And another one is this. You take the measure of the set where x and y are different. And it's 0. Got it? So in this case, what is that set with inequality? This is simply the set of 0 and 1. Here, be careful. This set has 2 points as the element. And the length of just 2 points in the real line is 0. Okay? So 2 functions are almost everywhere equal. And here, we can find an equivalent other definitions with almost everywhere equality. The first thing is this one. X and Y are almost everywhere equal on, of course, D. By the way, this is a notation. A dot E dot, almost everywhere. Got it? Almost everywhere equal if and only if. So it's kind of equivalent definition. X of S minus Y of S. You take the error and raise the error, absolute value of the error or modulus of error, raised to the power of P greater than or equal to 1, any real number. And you integrate this error on the domain. And if this is 0, and only if they are almost everywhere equal. And now let's apply this definition with, for example, P equals 2 in that case, in the above example. So what you do is that you integrate the difference squared over the interval 0 to 1. And what do you have? What is this function? This function is 1 at s equals 0 and zeros on the interval except the 2 endpoints. Got it? So you integrate that strange function 1 or 0, 1 on this interval, and that is 0. Okay? So these two functions are almost everywhere equal. Got it? And there is another one. If and only if this looks strange for every epsilon positive, as we always love for every epsilon positive, we consider the set similar to this one, but not exact inequality. We put some margin. And we measure the size. Okay? And this is 0. You may say that, wait a minute, are they equal? Actually, they are slightly different, but equivalent. See that? This is the same as measure, parenthesis, S in D. And what does this mean? What does this mean, by the way? This means two real numbers are the same for every epsilon positive. X of S minus Y of S less than or equal to epsilon, right? So this one is for every epsilon positive, X of S minus Y of S greater than epsilon. Now, this for every epsilon was inside the set after such that. Now you take this one outside. That is this equivalent definition. No problem so far. Got it? They are all the same. So I've just covered this part and that part. And also this one. Got it? Even though this infinity, I will correct it to D and D, 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 D. Actually, I was correcting this, but had no time to upload it yet. Okay. Okay. Anyway, the integral is not Riemann integral, but it's Lebesgue integral. That is related to the measure theory. I'm going to avoid it. Okay. So for the almost every equality, we first naturally defined it using the set, like this one. That is the definition. And equivalent definition is that one. But here, P could be any real number greater than or equal to 1. So actually, this definition is what? Has uncountably infinite sub-definitions. Anyway, and here goes the third one. Using for every epsilon positive. That spell, our magic spell. Got it? So far, so good. And these three equivalent definitions will be modified when we are talking about a sequence of functions converging to another function. And in that case, these three definitions become actually different. Their modifications become different. That's the key point. So here, from here, we are going to talk about approximate equality of two real functions. To precisely discuss that kind of argument, engineering or real-world argument mathematically, we usually construct a sequence of functions and show the convergence of the sequence to the target function called the limit function. Got it? So now suppose we have a sequence of functions. And we have a kind of target function x, in this case for simplicity. Let's say x. You can change it to y if you want. Now, usually when we approximate, usually no nth entry of the function is the same as x of s. Got it? Everywhere or almost everywhere. We just want to claim that for sufficiently large n, the nth element of the sequence of functions is very close to our limit or target function. What does that mean and how can we define that? So we introduce different definitions for this kind of situation. And as I told you last time, you already have been exposed to this situation when you are taking the signal gen systems course in your undergraduate program. There were the topics called Fourier series analysis. And there, one of the typical example was the square wave like this. So here we have square wave that is discontinuous. And even though last time I was taking this example to talk about x and that y are different functions, but they are almost equal. But here, what we are going to do is that we consider Fourier series representation of this x of s or y of s. And you know how to compute it. From that Fourier series representation, we construct a sequence of functions by truncating the series to a finite terms. So we take the first two nth terms. So our summation becomes from I equals 1 to n. And that becomes x sub n of s. And you've heard about, for example, Gibbs phenomenon. You also heard about some some sufficient condition called Dirichlet conditions, a collection of conditions called Dirichlet conditions, under which the Fourier series has some nice property, like at every discontinuous point, the Fourier series converges to the midpoint, and what the Fourier series converges almost everywhere to the original function, something like that. And the Gibbs phenomenon says that the difference of the error becomes smaller and smaller if you add more and more terms. So you have some knowledge about the sequence of functions. And you have some example in your brain where sequence of functions is almost the same as the target function. However, the limit is not the same as the original function, right? Now, in order to precisely discuss the convergence of a sequence of real functions, we introduce several definitions. Before we're doing that, we need the notion of metric space. And the metric space requires some definition about distance metric. So let's review some topics in the introductory analysis. So here we are going to talk about a metric space. And what is a metric space? It's a set with some function to measure the distance between two elements of the set. So suppose you have a set S, and you want to say that this is a metric space. In order to talk about that, you need some distance metric. So whenever you talk about a metric space, you must talk about a duet or a doublet consisting of a set and a function. And here, D is what? Usually, it has two inputs. You know what does that mean, right? This is a Cartesian product. So actually, D has two inputs, like X and Y. Ready? And usually, our distance metric is a real valued function with some special property. And mathematicians have kind of defined and found three properties for a metric D must be a distance metric. So this is not just any function. It must satisfy some property for the duet to be a metric space. And this distance, so a D, in this case, the arguments are functions, but you can just assume that you are given an abstract space S. Right? It could be any set. It could be a set of functions. It could be a set of real numbers. It could be a set of matrices, set of tenses, no problem. The first thing is non-negativity. So actually, this must be restricted to the R plus. R sub plus means that it's non-negative. R sub plus means it's strictly positive. Second one is that symmetry, which means that dxy is greater than or equal to 0 for all x and y in S. dxy equals dyx for all xy in S. And the third one is self-additivity, or by the way, here the equality holds if and only if x is equivalent to y or x equal to y. And I will talk about this equal here. It's complicated. But anyway, the third one is triangle inequality. And you know what does that mean? Suppose you have 3 xyz in S. Then distance from x, y, and z, yz greater than or equal to xz, right? Got it? This is the triangle inequality. And an abstract set and a metric satisfies those 3 conditions. It is called distance metric, and this space is called the metric space. And when you talk about equality, we usually use so-called equivalence class. Okay. Also here, x equals y means that they are actually not exactly equal, but in some equivalent class. We've already seen 2 functions x and y has what? Has this integral equal to 0. And we may define if these wholes, they are the same. And they are in the equivalent class. And also we may define just this one as the distance metric. Okay? For example, in that case, this distance metric actually tests whether x and y are almost everywhere equal when it claims distance is 0. Got it? So in this case, the distance metric says its distance is 0. Actually, these 2 functions are not equal everywhere, but almost everywhere equal. So we can a little bit relax the meaning of equality by introducing the equivalence class. So in this case, for example, given the set of all functions on the same domain, the entire set S can be partitioned to subsets called classes. And for example, in this subset, they are equal, for example, almost everywhere to xs equals 0, for example. On this subset, every functions are equal, for example, to the function x of s equals 1, something like that. Of course, here I partitioned the set S into, definitely in order to visualize finite subsets. Actually, you generally partition the set into uncountably infinite subsets. And in each subset, the members are actually different. However, in some sense, they are the same. Then each set is called equivalent class. Got it? This figure shows the Fourier series approximation. Here you see k runs from 1 to n. It must be 0 to n. Okay. In this case, the DC is 0, so probably that's why I removed that one. And I also do not have cosine because it's x of t is defined as an even function. Anyway, here you want to increase n and say or claim for sufficiently large n, this function with finite terms is almost the same as the original function. how do you want to define that one? And the first idea is this. As we have always done for a sequence of real numbers or complex numbers and its convergence, we start with for every epsilon positive. Okay, so we take some positive, possibly very small number, and want to check for sufficiently large n, blah, 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 such that n greater than or equal to n of epsilon. So probably here goes, there exists n of epsilon in the set of natural numbers such that n greater than or equal to n of epsilon implies something. So this part may define our first definition of the convergence of a sequence of functions. So how do you want to define? The simplest one is this. You have chosen epsilon. And what you do is that from your target, in this case, let's say x of s, okay, even though that is t. And what you do is that you want to compare these two and want to say that this is less than or equal to epsilon, right? But the problem is that there are many possible s, right? So the first idea is this. For every s in the domain, this holds. So you say for all s in the domain. So this implies that. Okay? What does this mean? You know how to remove this absolute value operator by putting what? Greater than or equal to epsilon, like that. Then what do you have? You add x of s to the three sides. And this means you subtract epsilon from the limit function or target function. So in this case, what do you have? Am I right? That is x minus epsilon for every s. And you add plus epsilon. Right? And then you check whether your nth function resides or lie inside these intervals. So you check this. Okay? And if this holds, then what? You may say or you may claim that for sufficiently large n, the nth function, x of n of s, can be approximated by x of s. Of course, in that case, your epsilon must be very small, right? And your n of epsilon could be very large. But anyway, if you can find n of epsilon for every epsilon positive such that that holds, then you may claim that, x sub n is very close to s for sufficiently large. And you name that as what? Uniform convergence. That is called uniform convergence. Why uniform? The uniform means uniform is due to this part. For all S in the domain, for all S in the domain, you have chosen a single absolute, and you have some upper and lower bounds, right, from the target. And for sufficiently large n, your function must be inside that upper and lower bounds. That is uniform convergence. And this is very, 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 very strong. Okay. And probably this is the most strong in your undergraduate or engineering graduate level real analysis, the most strong convergence definition of a sequence for a sequence of real functions. And if you have a uniform convergence, this is not the real analysis course, you have, so I will summarize, you have very good properties. If xn converges to x uniformly, of course, on some domain D, and of course, in order to talk about that, your every xn and x must have the same domain. Otherwise, your uniform convergence does not, cannot be defined. Now, suppose the sequence, your sequence of xn's must have the same domain with x for sufficiently large n, precisely speaking. But anyway, if you have this, xn converges to x uniformly on the domain D, then you have very nice property like this. For example, you integrate x on the domain, then it can be replaced by, of course, let me see, be careful. I must be careful. Yeah. Something like this. You may say that, okay, let me replace this one as limit x sub n. But you have the limit outside the integral. What does that mean? You change the order of two limit operations. So uniform convergence allows you to change the order of the limit. That's good. Okay. So it's very strong, and many of your sequences of functions of interest may not satisfy that one. However, if it satisfies uniform convergence criteria, then you have something very good. Okay, you have something very good. Under some mild condition, you can even differentiate x. Differentiation of x, the derivative of x can be found from the limit as the limit of the derivative of the nth function under some mild condition. Got it? So if you want to show that your function is very close to some another function, what you do is that you construct a sequence of functions. Of course, if you construct badly, then you may not have uniform convergence. But if you construct some function very cleverly, you have uniform convergence. And in that case, you can almost arbitrarily change the order of summation and integration and limit and limit, something like that. And you have something very good. During the last 20-some years, I wrote a small number of papers. And in one of the papers, actually, I proved that and used some statement like this. According to the results, and I put the reference, I can exchange the order of two limits because the sequence converges uniformly. Done. Okay. So probably all my study, taking real analysis, measure theory, measure theoretic probability theory, could help for me just to write that single line with confidence. Okay, I'm sure this is correct. And also, probably the reviewer of the paper believe that, okay, this guy is very knowledgeable and there is nothing technically wrong. That is very important, right? If the paper is technically incorrect, if a single line is incorrect, the paper can be rejected, right? So you need to show kind of credibility of your paper by stating that kind of line very precisely. Anyway, so uniform convergence is very strong and useful. However, many sequences of functions, even though they converge in some sense, they do not converge uniformly. That's the problem. They do not converge uniformly. For example, in this scale wave, the Fourier series does not converge uniformly to the original scale wave. Got it? Even though if you integrate this function on, for example, a single period, you have that result. But that result is not due to the uniform convergence. Okay, it's just due to the symmetry of sine functions and blah, blah, blah. Anyway, so this is the first mode of convergence, of definition of convergence. There are many different definitions. First thing is the uniform convergence. So as also this figure shows, you find a you choose single epsilon positive and put a band to find an upper and lower bound on some upper limit, upper limitation or lower limitation from the target function, and on the domain, your nth term for sufficiently large n must reside inside. Okay, that allows your exchange of the order of functions and blah blah blah. Here goes the convergence everywhere, and you may say that, wait a minute. When we talk about the equality of two functions, functions are equal everywhere was the strongest definition, right? And we had what? Almost everywhere. That is little bit relaxed definition. But I just told you that uniform convergence is strongest one, probably you will be meeting. And here goes the everywhere convergence. Strange. Now let's see the definition. Given a sequence of functions, xn, you converge, you claim the sequence converges to x everywhere. If for every s in the domain, okay, and here goes the statement, for every epsilon positive, there is n of epsilon in the set of natural numbers such that x of s minus y of s is less than or equal to epsilon. And you may say that, are they the same or not? The uniform convergence and convergence everywhere, it seems they are same. Is it true or not? It's not. If you remember correctly, in the uniform convergence definition, this for every s in the domain was here. Then what does this mean? You choose s first, and then you choose epsilon. And since you have chosen s, actually, this one is simply, xn and y. Now I understand why you have some strange face. Okay. Sorry about this. Yeah. So given s, this is just from a sequence of real numbers, no function at all, right? If you choose s, right? So at every s, which means that you have, let's go back to this, okay? So you choose some point first. And then if you cut here, if you increase the order or terms, then you just have a sequence of numbers, right? At each S. You have sequence of real numbers at each S. And at each S, that sequence converges. That's different from the uniform convergence. In the uniform convergence, you choose a single epsilon and put the bound for all S. But here, everywhere convergence means that you just check at each S in the domain whether the sequence converges or not. And you may say that here they look the same, but it's different. An example, I remember I had some example. Where it is? Okay. Yeah, I have an example. Probably where? Yeah, probably here. Too far away. I will just make up, okay? I'll just give you an example. Okay. So suppose your sequence, example of everywhere convergent sequence of functions. That does not converge uniformly. Okay. So if I provide you such an example, you'll assure that these two definitions are different. So here goes the sequence. I hope I still remember that example. So let's restrict our interval at the domain, common domain, to the interval 0, 1. And am I correct? Just a second. Just a second. I'm not sure I still remember that. Let's say our S, x of S is simply this simple function, okay? Yeah. And what I do is that I define x of n as non-uniformly convergent function. How did I define that? I just do not remember the example. Let me just find a good hint. Oh, okay, got it. Yeah, let me little bit modify this. Okay. So suppose we are interested in the functions on this open interval, okay? And our x of S is simply this, got it? Now, we define x of n as this one. Got it? So it's a strange sequence of functions. And let's see what happens if you increase n. Okay. So let me say n plus 1 to make everything simple. So what is the first element of this sequence? X1. X1 plus 1, sorry. X1 looks like this. Here goes 1/2. And this is 1, and you have 2. This is x1 over s. Got it? Right? Now, what is x2 over s? This one goes to 1/3. And this height becomes 3. Suppose you have this kind of sequence of real functions. Now, let's check whether it converges everywhere on D or not. In order to do that, let's consider a real number between 1/2 and 1. And as you see, whatever s you choose, you always have 1 that already equal to the target function on that s, right? Now, we are interested on, for example, some number here. And let's choose some arbitrary s on this interval. For example, 1/3. What happens? At 1/3, your x1 of 1/3 is what? First, 2, right? But suddenly, after n increases, it goes to 1, and it is 1 after that, right? So if you choose any number greater than 0, then you can always find sufficiently large n, because this n, 1 over n plus 1, 1 over n plus 1 converges to 0, right? So you can always find, given s, you can always find some n, capital N, such that lowercase n greater than or equal to that capital N, you have just x of n equal to x, right? So this sequence converges to the target everywhere on D, right? However, let's check whether this sequence uniformly converges to the limit. So what you do is that you have to choose some epsilon and put some plus minus epsilon bound. And as you see here, you can never find such capital N for every epsilon positive, because this part, even though you have smaller and smaller region on the domain, your function and the target has difference, bigger and bigger and bigger. You can never put the error to the function inside this small bound, right? So this example shows that uniform convergence and convergence everywhere is different. They are different. Then they are different, but which one is stronger? You can just see that if sequence uniformly converges, then it converges everywhere on the domain. So you have this part, okay? Uniform convergence on the domain implies everywhere convergence on the domain. However, the converse is not true. Got it? So you know how strong uniform convergence is. And that strength allows us to interchange sometimes the orders of two limits. Interchange limit and integration, something like that. Got it? Now, you've seen convergence everywhere. That means at every point on the domain, you have a convergent sequence of real numbers, right? Because as we've seen in random process, right? If you fix S in the domain, then you no longer have function. You just have a sequence of real numbers, right? So that sequence, if that sequence converges, then you are done for the convergence everywhere. Now, as you've seen here, we are going to relax the convergence, everywhere convergence to almost everywhere convergence. Actually, that is easy because as we've done for the everywhere equality of two functions, and we relaxed it to almost everywhere equality of two functions, we can do almost the same thing very straightforwardly. And here goes the everywhere, almost everywhere convergence of a sequence of functions. So again, we have a sequence of functions x sub n having the same, for example, domain as the limit, that is D. And what we do is this. As we've checked for the everywhere convergence, we construct a set. And we may construct two sets, like first, okay, set of S such that x of n of S converges to X. If Xn converges X everywhere, if and only if this equals D, right? We know this one. Too simple, right? Xn converges to X everywhere, if and only if for each S, the sequence of real numbers converges to the number X of S. And these two sets are the same, right? And we just relax this equality, set equality to measure equal measure. So the definition would be measure of this set converges to S equal to, measure of D. But be careful. The reason why we don't say is that the measure of D may be infinite. That's why we love this equality. Got it? The same for the, actually, the almost everywhere equality. So where it is? Yeah. Now you see here, I didn't say equal measure of the set with equality equals measure of D, because measure of D may be infinite. But since this course is on the probability course, the probability measure is very special in that our sample space has special measure called probability measure. And the probability of entire sample space is finite to 1. So that's why in many probability courses, they love equality and equal to measure of the sample space, which is 1. But be careful. So far, the domain may be, for example, the entire real line. In that case, measure of that one is infinity, and we want to avoid infinity. That's why we love this. So precisely speaking, I should not talk about where I am. Okay. Yeah. I should not say this. Okay. Probably I would say that, okay, this is equivalent to Xn of S converges to X, does not converge to X is the empty set. And I put measure and having this. Okay, not that one. Got it? So this is almost everywhere convergence definition. Okay, so you find the set of S, a subset of D actually, where the sequence of real numbers does not converge to the limit. and that set has measure 0. Then you may assure that, okay, my sequence converges almost everywhere. Now, let's see whether this example, in this example, the sequence of functions converges almost everywhere. Almost everywhere? Yes, because it converges everywhere. Now, let's little bit relax that one and consider this one. Now, our domain is closed interval 0, 1. So here, 0, 1, and suppose your limit function is just 1, okay, on this interval. And your x of n is the same as that one before. But now, it also equals to 1 here, and equals to n plus 1, something like that. Got it? Now, let's find the subset of D such that xn does not converge to x. What is this set? What is this set? Of course, at 0, right? At s equals 0, now it should be considered because we included s 0 to s, right? To D. Now, at s equals 0, if you increase n, what happens? It diverges to infinity. So this set must have 0. What else? Nothing else, right? So you have the subset of D on which the sequence of real numbers does not converge to the limit is what? A kind of singleton set that has single element. And what is the length of that set? 0. So what can you claim? This sequence of functions converges to the limit function almost everywhere. However, it does not converge everywhere. Why? Because at s equals 0, it does not converge to the limit. Got it? So we kind of pave the path to almost everywhere convergence of a sequence of functions. Now, you remember that, when I was just given 2 real functions and when I defined the almost everywhere equality, I could use integration. And I could take out that for every epsilon positive outside, but the definitions of 3 of them were equivalent. Can I have something similar? So let's first check that integration thing. So here goes the definition. What you do is this. You have a sequence of functions and a possible target or limit function. And what you do is that you consider this integration. This is motivated by x equals y almost everywhere on D if and only if what? Integration of the error raised to the power of p greater than or equal to 1 is 0, right? So motivated by this definition of equality everywhere, almost everywhere, you want to somehow define a sequence of functions converges to a limit, right? So you just copy that one. And now see that when n is some finite number, your integration could be some non-negative number, right? So how many real numbers do you have? You have countably infinite real numbers. And you can construct a sequence of real numbers here. And you may want to say that, if this sequence are not equal, but converges to 0, then I can claim or define or introduce a new definition. And it could be the same as almost everywhere convergence. Is it true? Surprisingly, they are different. Okay? This is not equivalent to almost everywhere convergence. This is totally different thing, and we will see the example. So what happens is here. That is called the convergence in the pith mean. And you remember, I've heard something similar. Yes, you are right. We've already seen, given a sequence of random variables and a random variable, we had something like this. And we defined it as a convergence in the second mean or mean square convergence, right? Actually, what's the difference between these two? They are mathematically the same. The difference is that now this 2 is replaced by more general real number p greater than or equal to 1. So this is called the convergence in the pith mean. Okay? Convergence in the pith mean. If p equals 2, it's mean square convergence of a sequence of real functions to a real function. And this definition is interestingly different from almost every convergence. Okay? Their prototype, the almost everywhere equality, and kind of pith mean type equality, they were the same when you are talking about two real functions. However, now you change this part as a sequence of functions and just modify these two definitions, then you have totally different definition of a convergence of a sequence of real numbers. And now let's see why they are so different. And actually, this example we've already seen gives us some idea. Now let's check whether this sequence of functions converges to x in the second mean, for example. So in order to do that, we subtract them and take the absolute value, and we are going to square it. Then what is the integral of that one? So let's integrate xn minus x raised to the power to the n and compute. Then what is your integration interval? Just 1 over n plus 1. And what is your difference? N squared. And this blows up. Right? So this sequence of functions, even though it converges to the target almost everywhere, it does not converge in the mean square sense. It does not converge if you raise bigger than 2, still does not converge. And it converges only when p equals 1 in this case. No, even in that case, it is not. If p equals 1, then it converges to 1, not 0, right? So this sequence of functions does not converge to this sequence in any pith mean greater than or equal to 1. However, it converges almost everywhere. So now you see that almost everywhere convergence is totally different from the convergence in the pith mean. That's why I have this branch. So these definitions imply uniform convergence implies everywhere convergence implies almost everywhere convergence. However, convergence in the pith mean just simply is not related to the almost everywhere convergence. Got it? Which means uniform convergence does not imply, uniform convergence, I should be careful. Anyway, the last thing is another alternative definition of this one. And we remember for the equality, almost every equality, we had something equivalent. What was that? for every epsilon positive, right? And we find the subset of D where X is different from, Y, and we take the measure, and this is 0, right? So we do the similar thing, and here goes the definition. Yeah. So we take for every epsilon positive first, and then we of course measure the subset of S. But now for each n, we have a function to be compared with our limit. So, and in general, this greater than or equal to epsilon means not equal to 0, right? Yeah. This set is what? Does not have measure 0, but small, right? And also, if you change n, how many this measured subset do you have? Countably infinite. So now you have a sequence of real numbers, and probably you want to set that converges to 0. Okay. So here you have this one, and be careful. This one becomes some sequence of real numbers because you have measured the size of this subset. And you may say that, okay, so let's check whether that definition is different from, for example, almost every definition, or almost every convergence definition, or convergence in the piece mean definition. And since we do not have enough time, we can just check whether this almost everywhere convergence implies, by the way, that is the convergence in measure we call. Let's check this part. So we've seen already that in this example, Xn converges almost everywhere to S. Now, in order to check whether this almost everywhere convergence implies convergence in measure I just defined, let's construct a sequence of measured subsets of D. So let's see. You choose some epsilon, some small number, and you construct a set of D on which these two difference is bigger than epsilon. And let's say epsilon is 10 to the minus 1, for example. Then what would be the subset? That is this interval, right? Now you measure the size of the interval. That is 1 over n plus 1. Now, the sequence of real numbers, 1 over 1 plus n, converges to 0, right? For that given epsilon equal 10 to the minus 5. Now, you choose any epsilon positive, 10 to the negative 10 million, 10 trillion, 10 Google, anything. Still, what happens? You have the sequence of the subsets 0 to 1 over n plus 1 as the non-convergent or none less than or equal to epsilon subset, and the length of the subset still converges to 0. So you've just seen in this example, almost everywhere convergence may imply convergence in measure. And that is actually true for every case. And also, you can show that if a sequence of functions converges in the piece mean, and then it implies convergence in measure. So you have something like this. You have uniform convergence, everywhere convergence, almost everywhere convergence, and convergence in measure. And you have convergence in the piece mean. It looks like you have a single definition, but actually how many definitions do you have? You have uncountably infinite, because P could be greater than or equal to 1. So that's all for the mode of convergence of a sequence of real functions. We haven't yet arrived at our final station where we have to study four important modes of convergence of a sequence of real random variables. We haven't yet. We will see that in the next week. Okay, that's all for today.